We also need to design for what we call, aptly in our engineering circles, the Sharknado events. It's a situation where you have multiple catastrophic events happening at the same time.
Well, it's good to have you, Tariq. We have worked together for a long time, but our listeners might not know you. So our guest this week is Tariq Amlani, mechanical engineer and health sector leader based in Victoria, BC for Stantec. Tell us about yourself. Like, what do you do on a day-to-day basis? What kind of projects do you work on? Tell us a little bit about your world.
Yeah, you bet. Thanks, John. And great to be back with you again. Always a pleasure. It's really fun. I say often that in my role, no 2 days are the same. Every day is a new adventure of where it takes us. My primary focus within the organization is on the design and delivery of health facilities all around the world. Everything from acute care to outpatient to long-term care, medical office buildings, the whole gambit of everything health related. I also do support often other BOUs and other sectors, depending on where that specialty expertise is required. I bring a lot of experience with modular and prefabrication, and deep experience in mechanical engineering design, and as I'll relate today, decarbonization. Yeah, happy to be here.
Awesome. So the reason we brought you here today, which you're well aware of, is the post on our ideas blog you authored recently on decarbonizing hospitals. We ended up titling it, Why Decarbonizing Hospitals Smartly is Better Than Electrification for Healthcare Design. So I wanted to kind of talk about some of the ideas there and get into that a little bit. But the first thing I wanted to understand is, because we're sort of focusing on Canadian healthcare today, where is the sort of impetus for hospitals to decarbonize coming from? Who is, saying, okay, this is something we need to do right now?
For sure. It's really coming from all levels. So we've been designing healthcare facilities for many years now, and the idea of a high-performance healthcare facility is far from a new one. Hospitals operate 24/7. They're highly intensive in their energy consumption. We've always known that it's important that we design our facilities to the maximum performance available. In recent years, the push for decarbonization has been elevated on many fronts. Climate change, the impacts of climate change are really starting to become front and center and apparent in our day-to-day lives. When you actually look at the research, healthcare facilities around the world contribute to global emissions by about 5% of the total global emissions. So 1/20th of the overall emissions in the world come from healthcare facilities. So there's a lot of attention on decarbonizing healthcare facilities. Specifically, though, there's a couple of drivers. In the Canadian context, carbon tax is real, and it's having significant impact on our operational cost of our facilities. Politically, there's a lot of pressure to decarbonize, and that's creating new tariffs, new regulations, new constraints on funding mechanisms to say, yeah, we'll give you the money for the hospital, but it has to be a decarbonized or it has to be an electric hospital. So that's also pushing. And then political will of the voters. A lot of the users of the facility, a lot of the communities are seeing the importance of decarbonizing, and that's creating a groundswell of demand for decarbonized healthcare facilities.
Great. So, and you're getting this also from your clients. That this is something that you see in the marketplace, where more people are, or more potential clients. There's more requests for expertise on how to decarbonize healthcare. When you sort of get into these conversations, how do you explain what the difference is between decarbonization and electrification? Because I think you told me that sometimes you sort of hear people asking about electrification before they've really asked about decarbonization.
For sure. Yeah, it's interesting. When you talk to the clients and you talk to the policymakers, you get a good understanding that their drive is to decarbonize facilities. That's their end goal. However, when you read the actual approval notice or the mandate letter that comes with the project, or the business case even, it says the healthcare facility shall be fully electrified in order to decarbonize. So you start to learn pretty quickly that there's an inherent assumption that electrifying equals decarbonization. And especially in Canada and in many of our provinces within Canada, there's rightfully so that understanding or that belief, because a lot of our electricity comes from hydroelectric. A lot of it comes from wind, and some of it comes from solar. To a large extent, some of it even comes from nuclear, and that's seen as low carbon intensity fuels. There's a issue though when you really get into the detailed design of it, and we start to realize that in many of our regions, our electrical demands exceed our available electrical generation capacity of these renewables. And a good example is in British Columbia. For the last 3 years in British Columbia, we've been a net importer of electricity. And a lot of that electricity is coming from Alberta. So even though in British Columbia, most of our electricity is generated by hydroelectric, which is a relatively low carbon impact or carbon intensity. The electricity that's generated in Alberta, the majority of that is actually from coal or gas-fired petroleum, natural gas. So as we're importing, especially on the margin, where if we add an additional project, we're already at capacity. So in order to feed the electricity for that additional project, we're importing our electricity for that. As it currently sits in our market, we're actually having a higher carbon intensity at the margin. And that's not always captured in the business cases or in the averages that are used. And it's important consideration. On that, there's an interesting article or paper out there. It's called The Big Switch. And it looks at, it's from the Climate Institute of Canada, and it looks at where we need to go from where we currently are to maintain sustainable renewable electrical infrastructure. And it takes into account more than just healthcare facilities and really more than just buildings that are electrifying. It takes into account that there's a huge push for electric vehicles that's increasing the demand, the electrical demand on the grid. There's many LNG plants around the country that are using electricity to run compressors, and there's major demand that goes with that. And then there's obviously the institutional buildings and the healthcare buildings, but there's also residential buildings that are coming online that are electrifying, just to name a few. So what that report studies is that our capacity in 2050, our electrical capacity in 2050, needs to be 2 to 3 times larger than what it is right now. And in order to get from where we are in 2020s to where we need to be in 2050, we need to grow at a rate that's 3 to 6 times faster than how we're currently growing our networks and our electrical capacity. So when we have these conversations with clients, and there's many facets to this discussion that I'm sure we'll explore here, but one of the biggest ones is, okay, well, yes, in the future, the anticipation is that we will have a clean electrical grid, and it's actually going to be a North American grid that we're going to be able to rely on. But where we are today does not necessarily give us that benefit of electrification equals decarbonization. Sometimes if the decisions we're making right now to electrify actually increase our carbon emissions compared to a business as usual case for a healthcare facility in 2024. So we're not saying by any means, let's not electrify or let's not plan for that. It's very important that we have a roadmap so that once the grid is resilient enough and has the capacity for us, that we can attach to that and we can realize the gains and the potential carbon decarbonization opportunities. But we really do need to think about where we are now and what the right decisions are for today and how we're going to pivot from where we are. How we're going to roadmap from where we are today to where we're going to be in the future. Does that help?
Yeah, it does. So it's in a way, I think the difference between how you're thinking and sometimes how the client is that this is going to be a multi-decade process in your mind, where these other elements, the grid, the power supply in the province, the electrical infrastructure is all sort of evolving, and the client is actually thinking this is a one-time deal, right? When they start these conversations. What about just we kind of gloss over this a little bit. What makes healthcare different? Yeah. In a lot of my conversations with health designers, we talk about how hospitals really need to be more resilient than other buildings, and then we have different building codes for hospitals and
For sure.
different standards for them. So explain that a little bit and how that influences decarbonization.
Yeah, absolutely. So there's a inherent assumption that our society has that our healthcare facilities are going to be there for us when we need it. And in any modern building, when we design it, we will run an energy model, and we'll look at climatic data, the typical climatic data, and we'll run a model, and we'll say, okay, over the course of the year, how is this facility anticipated to operate? What's the energy consumption associated with it, and what is the carbon emissions associated with that? In parallel, as we're designing, we're figuring out what the peak loads are and the capital costs associated with that. It's a typical design process. What's a little unique about healthcare facilities is the requirement for resiliency and continuity of operations. And I should really clarify, when we say healthcare facilities, there are a whole spectrum of typologies of healthcare facilities within the health sector. Everything from, a specialized acute care center. A good example is right now we're helping to design the hospital for sick children in Ontario, the Sick Kids Hospital. So this is neonatal intensive care units where you're going to be performing surgeries on newborns. That is probably at the highest end of the level of continuity of operations and resiliency that we anticipate in our facilities. It's not acceptable to have a system go down if the power goes out, or if there's a cold snap, or if something happens. We need those facilities to operate no matter what. On the other end of the spectrum, we might have a outpatient doctor's office, where if the facility goes down because of a power outage, or if there's something going on there, we can safely evacuate the building, and we can pick up business again in the future once that's gone. So I should clarify that there's a whole spectrum. Really, what we're talking about today is the acute care facilities. Some might call them the Class A facilities when you're looking at some of the building codes and the way that works. So for these Class A facilities, number one is resiliency. So if the building has an electrical supply, which all buildings will, we need to say, okay, well, if that electrical supply to the building goes down because, let's say, there's a tornado or a storm or something happens and we lose that electrical service, we need to have an automatic changeover to an emergency power system on site. And typically, that's a diesel generator. So that's something we'll think about. A modern hospital today often will have gas-fired heating systems. And if that gas line to the building fails for whatever reason, there needs to be on-site fuel storage to back up that heating system. So we often have a propane tank on site, and that's the way we handle that. So there's this continuity of operations, which is important, and we'll come back to that in a second. We also need to design for unforeseen conditions. So I mentioned how the energy model kind of looks at what the typical conditions that we expect in the building are. But we also know that often, like I'll give Vancouver, British Columbia as a good example. In Vancouver, British Columbia, the winter design condition in the building code is -9 degrees Celsius. Well, last year in January of 2024, we hit -14 degrees Celsius. Well, we still need to make sure the hospitals can operate. Just because it's colder than what we expect in the building code, we still need to make sure we have that resiliency. And we do a climate hazard analysis, and that's how we figure out what we need to design for. So we'll design for it. We won't necessarily model in our energy consumption estimate for the year that we're going to run at that point, but we make sure we have the horsepower to be able to run at that point in case we need to. Another nuance of the healthcare code for acute care facilities is the ability to operate in the event of a pandemic. And it's interesting, this was a code change that came in 2010. When in 2020, when the pandemic hit, if your healthcare facility was built in the last decade, you were in a really good position to be resilient to handle that. And the way we handle that condition is we turn all of the air that's coming into the building and we make it all fresh outside air, relatively fresh. We call it fresh outside air. And that way you're not recirculating air from within the buildings. Whereas in normal operation, you're recirculating about 2/3 of that air. You're filtering it and recirculating it. So you need to be able to design for this condition where you're bringing in all outside air. And we also need to design for what we call, aptly in our engineering circles, the Sharknado events. And it's a situation where you have multiple catastrophic events happening at the same time. So in a simple example here, it could be a polar vortex. So it's minus 14 degrees Celsius outside instead of minus 9, which is the building code condition. And there's a pandemic. So we need to go to 100% outside air. The magnitude of impact on the design load is significant. And I just ran an exam or a study for a client, and that Sharknado event, it increased our peak heating load by 2.5 times, from a 100% heating load to 250% was the heating load. So even though we don't model that we're actually going to have to operate in that condition, we need to make sure we have the infrastructure that's able to operate in that condition should it happen. And the pandemic was a great example that we were very happy that we had those facilities in there. So just to give you an example of the specific nuances that we need to think about here, and I can run through some other examples of when we try to decarbonize, then how there's some unintended consequences that emerge when we try to fully and blanket electrify our facilities, but still while maintaining the continuity of operations in these catastrophic conditions.
Right. Yeah. So there could be, you could model an electrification project for a hospital that makes a lot of sense in the day-to-day operations, but because we're talking about healthcare, we have to design for more extreme situations and resiliency, 24/7 resiliency, and that doesn't really click very well with sort of what's possible with electrification these days. So what are kind of what's the more realistic path for decarbonization right now that sort of allows for electrification and sort of a future where we're more electrified as a society?
For sure. So I'll give an example here on a study that we just ran for a client that wanted originally the mandate was for a fully blanket electrified building hospital. And one of their keys was they didn't want to have a natural gas line come into site. Full stop. Fully electric, no gas to the building. So what's interesting is in order to do that, the mandate was to look at electric boilers, put an electric boiler instead of a gas-fired boiler. And for that specific building, it was about 7.5, 7.2 megawatts of electrical load that we had as that Sharknado event, that worst case scenario. And it was funny there. Yeah, that's that 250% magnification of the peak electrical or peak heating load. So we needed to add about a 7 megawatt electric boiler in. So the first issue when we did that was the electrical service size to the building went from 1.8 megawatts in that condition to 9 megawatts. So there was a challenge in even getting the electrical service from the utility that was big. They kind of laughed at us. They said, that's how much power the whole city uses. What do you mean you need that for the one building? So that was a challenge, but it was surmountable. The second issue was, though, in a typical gas-fired heating plant, you've got propane on site as your backup fuel supply. Well, with an electric boiler, if you're going to have that as your primary heating source, in order to back it up, you need emergency generator size to back that up. So in that scenario, the generator load for the building went from 1.1 megawatt to 8.3 megawatts. So we added 7.2 megawatts of heating load. So we had to add 7.2 megawatts of boiler load. And when we modeled it, when we looked at what conditions do we expect to operate in, that additional horsepower that we had in the plant that was taxing the service size and was taxing the generators, it never got used because we don't assume that we're going to have a pandemic, and we don't assume that we're going to have a polar vortex. But what did show up was when you have an emergency power plant, a generator plant in Canada, serving essential services for a healthcare facility, that generator plant needs to be tested every week for an hour. And it needs to be tested every month for 4 hours. And it needs to be tested every year for 8 hours. Well, the carbon emissions from testing the generator plant actually surpassed the carbon savings that we had by going from a gas-fired boiler in a modern high-efficiency hospital, because we don't use that gas boiler very often. But to go from a gas boiler to a fully electric boiler, the savings were less than the additional carbon of the generator testing. So that was a challenge. And so the way we approach it, to answer your question, to come back to it, what do we recommend now for 2024? What we're saying to a lot of our clients is, okay, let's still electrify. Let's electrify for that load that we anticipate to happen in the normal condition. But if there's a polar vortex, if there's a pandemic, if there's a Sharknado event where it's the polar vortex and the pandemic at the same time, or other examples of simultaneous catastrophic events, how about for those conditions, we still have a boiler plant, and that's when we turn the boilers on. When we need the additional unanticipated conditions, we've got a carbon-based fuel that we can lean on. And in that case, we don't need to tax our generators and the testing of the generators. And we don't need to tax our electrical service size for that 250% condition. We'll still put additional electrical load on the building because we do want to decarbonize as best we can, but we'll use it in those conditions where it's normal operations, and we're going to see it. It's interesting in this example that we did when we looked at the model. It's actually funny. In the coldest 10% of the year, which is the coldest 36 and a half days, so call it a month, we're at 50% of our peak heating load. And when you look at the coldest 1%, which is the coldest 3.65 days, if you will, we're at 70% or less than our peak cooling load or heating load. It's only in the coldest 1% of the year that do we see our heating plant go higher than 70% of its normal design load, which is staggering to say when we right size our systems. So it's very rare. These small duration events really add a lot of peak load onto the facility. So we're saying, let's right size based on the duration load. Let's look at what makes sense for the most utilization of the facility and find that sweet spot for how we size it. So we're mostly decarbonized, but not fully decarbonized. That helps.
Yes, and we have that. We have a graph, I think, of the.
That's right.
We have a graph of that situation, I believe, in the
blog.
In the blog. That it makes it a little bit easier to understand. It's fascinating. So, and one thing you mentioned that I also I think is a great anecdote was speaking to the local electrical utility and telling them the kind of electrical demands you would need to have in a peak condition. That to me is really interesting because I think one of the things we talked about is that just the utilities and the grid are not there in most places to support this 100% electrification yet anyway, right? I mean, in a lot of places that they're just not ready for that. Is that
That's right?
Fair description of things?
Yeah, absolutely. On your question about the utilities and the service, and it's interesting here because we have a really strong power group within Stantec, and we design substations and transmission lines. That's one of the things we do. Sure. And in order to provide some of the demands that we're talking to for these facilities, you literally need to design a new high voltage substation, 350 kVA or something like that, knock it down to 25 kVA, distribute it to the site, and then have a higher voltage or a medium voltage distribution system on site. We would love to do this for these clients. It's one of the things that we do, and we're really good at it. It just doesn't make sense when you look at it and you start to look at the costs that you're coupling onto these healthcare facilities. And we're seeing a major issue right now, especially in Canada, where healthcare facilities have gone from the typical $1,000, $1,200, $1,800 a square foot. We're starting to see $2,500 a square foot, $2,800 a square foot, $3,000 a square foot. So more than doubling the cost of these facilities. And it's becoming to the point where it's untenable. The project can't proceed. It just doesn't make sense. So we need to work together with the client and with the utilities to figure out how do we achieve what the client's looking for? How do we create a map towards a future decarbonized community without having these costs and these capital burdens and these commercial issues come up that make the project untenable?
Yeah, that's great. That makes a lot of sense. one thing we talked about in the blog that I think is interesting is the changing climatic conditions, and that what might make sense for 2030, 2040 might not make sense in 2070, right? Or 2080, I think is the example we used, of a worst case climate scenario. How does that influence what we do? I mean, is that, oh, how can we sort of future proof these projects? How do we allow for that?
For sure. Yeah, no, it's a very interesting question. And a lot of thought power and thought energy has gone into what do we do about this? So the overall trend, the global trend, is that the Earth is warming. Now, with that, there's a couple of things. So right now, when I size a cooling system for a facility, I need to think about, well, is this cooling load going to be enough for the future? And it's tremendous. When you look at the loads, and we talk to our climate scientists within Stantec, and we look at the models, it's terrifying to see how significant the increase is expected to be. There's a couple of different scenarios that we map out depending on how much mitigation of carbon emissions humanity has as a whole. But we need to decide, and it could be double, sometimes even triple the cooling load that we see today is what we're going to need in the future. And it's interesting because sometimes a client will say, well, I'm only going to get one chance to build this. So put all that infrastructure in now in order to accommodate that future condition. And you look at it and you say, well, I can, but you realize that 10 or 20 years from now, I'm going to need to renew that equipment from a maintenance and a life cycle condition, and you're not going to have even needed it yet. So there's a bit of a disconnect that says, well, do we really need it? Does it really make sense to do these things? So what we're often doing is we're saying, okay, well, let's look towards modular energy centers and systems that we can add capacity to in the future if and when it's needed. And there's that saying that a dollar today is worth more than a dollar tomorrow, and there's certain things like that allow us to help rationalize the logic behind it on the capital side and even on the maintenance and operation side, because now you don't need to maintain and operate it for all these years that you're not going to be able to use it. Now, that said, there's other parts of the systems like pipes and shafts, ductwork above ceilings, terminal units, things that are very difficult to get to in the future, especially in an operating facility. There, we're saying, let's really take a close look at what those future conditions might be, and let's consider increasing the size of that infrastructure now. It's going to be so hard to get to in the future. It's a relatively low marginal cost to increase the size of that pipe. It does add up, though, when you add the space for that pipe and the electrical connections that are impacted, and all the things that trickle down. So you need to be mindful about it. But if you do it right, you can still give yourself that resiliency to accommodate the future scenarios with the hard infrastructure, but the active infrastructure you bring in the future, and you plan for growth of an energy center or certain areas where you can do things, and also accommodating future technologies. A great example is air source heat pumps. Their technology is rapidly evolving, and we're being able to now generate domestic hot water using ambient air and an electrical connection. So providing ourselves some opportunities to accommodate that in the future and accommodate future technologies, but without suffering the intense capital cost that comes with making those decisions now.
Great. And that would, exactly what you're talking about, would that tie into something I believe you told me about called a carbon transition plan? Is that sort of how they can, if they don't plan exactly for the future, they know what they're looking for in terms of making those decisions, right?
Yeah, for sure. I'd say it's similar but different. These are all interconnected conversations and concepts and design details. What we're talking about here is probably more under the umbrella of climate resiliency and understanding that. When we think about when I think about the carbon roadmap and the map, or the roadmap to neutrality, what I see is really great. A really great example of that is so the healthcare design standard for mechanical systems in Canada. It's a code called CSA 317.2. It's a standard called 317.2. It's actually out for public review right now. And we're seeing the draft wording that's in that standard. And then the next version of that standard is expected to drop either later this year or early 2025. And there's an interesting clause in there, and it says, healthcare facilities should design for net zero carbon emissions on day one. Where they cannot provide net zero carbon emissions, they shall provide a roadmap to carbon neutrality in the future. So it's a really good acknowledgement that if you can, go carbon neutral now. If you happen to have the resources, and there's other technologies out there like battery storage or geothermal exchange systems that really give you a lot of resiliency and give you a high coefficient of performance, or we're seeing some passive house hospitals pop up, and we're seeing there's different things out there that if you can really get your demand down low enough and you can achieve carbon neutrality on day one, absolutely go for it. If you've got the means, the capital, and the resources to be able to do that, you should, but not shall. They're not going to mandate it because they realize that there's a recognition that if you say shall, some projects just can't. It's just too expensive. And it would actually mean that we weren't able to develop those healthcare facilities where we do need those facilities now. But if you can't, you shall then create a roadmap to get to carbon neutrality. So is the anticipation that in the future the grid is going to be mostly based on renewables, and there's going to be a lower carbon footprint, and then you can put some on-site renewables to offset any carbon emissions associated with the transmission losses and things like that? Are you going to look at future district energy systems in your neighborhood? Is there an anticipation for a different technology to come into place? Spend some time during design to think about what that is, because once you get your head around how you're going to do that, there's a couple of nuanced design details that you can accommodate that make your lives a lot easier. There's even a project that I'm looking at right now where the original concept plan did not anticipate an electrified facility. And in the final business plan that was approved, the ministry said, thou shalt provide an electrified facility. Well, when the designers went back to add all of the space that you needed for the electric boilers and all the infrastructure and the generators, it ended up in a spot that had a tremendous impact on the clinical operations of the facility. And the hospital's kind of handcuffed. They're so far down the planning process that they can't really restack and redesign the building at this point. So they have to suffer the impact of having all this gear, this unintended gear, where it's not ideal to have, and it's going to have an impact on clinical operations for the life of the building. Had they known early on in the design, had they had a roadmap to carbon neutrality at the early design stage and said, even though we're not going to do this today, eventually we're going to need this, so let's restack it and let's give ourselves a little bit of space here or an ability to grow in this zone here, it could have been taken into consideration during the clinical planning stage in concert with clinical planning, and we would have been able to most likely avoid that situation that they're in now.
Very interesting. Tariq, I like that you incorporated the other blog that we worked on together in the conversation where we talked about the new
CSA.
New CSA code. Well, Tariq, fantastic. I think you really took things to a nice place there where we can call it a day. Can
I add one more thing, if I may?
Of course. Yeah. Of course. We're still rolling.
And feel free to edit this out at the end if you need to.
Okay. No, that's fine.
I'm going to say this. I'm going to say this on behalf of my kids, and it's probably not even relevant, but I feel the need. If you enjoyed the podcast and the discussion here, please ring the bell and hit like and subscribe.
Yes. Thank you. We've never done that before. We should bring you aboard for our podcast marketing.
That's funny. I hang out with my kids enough to know that that's a thing.
Yeah. Oh my gosh. Yeah. Excellent. I think awesome. You combined useful marketing and a dad joke in one swoop there, Tariq. All right. Awesome. Thanks so much for joining us.
Thank you for having me, John. Always a pleasure. Looking forward to the next.
Cool.